Hi everyone, welcome to my YouTube channel SN Classroom. So in this video we are going to discuss about maximum flow problem using Ford-Fulkerson algorithm. So what is maximum flow problem? So before going to see the actual problem, we will see the introduction. So it describes maximizing the flow in a transportation network. If you take any kind of network such as computer network, communication system or a pipeline system, definitely it has some nodes, n number of nodes. So from one node to another node there will be a flow. Okay. So in maximum flow problem, from the source node to destination node or sink node, what is the maximum flow through some augmenting path? So this is described by the maximum flow problem, and it is represented by a connected weighted diagram. So why it means connected? Connected means all the nodes are interconnected with each other. Weighted means definitely all the nodes will have some weight. And digraph means directed graph, means it has some arrow marks. So it is a connected weighted digraph with n vertices from 1 to n and set of edges E. Okay. What is edge? From one node to another node there will be a path, and that path is called edge. So the properties of maximum flow problem are: first one, it contains one source vertex and one destination vertex, which is otherwise called sink. How to identify a source node and how to identify a destination node? If any node which does not have the incoming edge, that is identified as source node. If any node which does not have edge, that is outgoing edge, which is called a destination vertex. Understood? So the node which does not have the incoming edge is called source, and the node which does not have the outgoing edge is called sink node or destination node. So in between source and destination node there may be some other vertices which are called as intermediate vertices. The weight of each directed edge is called edge capacity. So in the examination point of view, in your examination you will be given a problem or a digraph with a n number of nodes along with its edges. They will give the capacity, edge capacity. That is the original capacity of edge. So capacity means a numerical value which edge has. So this is the edge capacity. So a diagram satisfying all these properties is called flow network. And let us see the example of flow network. So assume this is a network or a diagram which has source node and sink node. So source is 1 and the destination or sink is node 6. Okay. So why it is source? There is no incoming edge. And why 6 is considered as sink? There is no outgoing edge. Fine. So in between 1 and 6 there are some nodes 2, 3, 4 and 5. They are called intermediate nodes and they have edges. Each edge has its own weight. Now let us see the flow conservation requirement of maximum flow problem. So what is flow conservation? The sum of weights of incoming edges of all intermediate nodes must be equal to the sum of weights of outgoing edges except the source and destination node. So except the source node 1 and destination node 6, the intermediate nodes 2, 3, 4 and 5 should have the incoming edges, whose incoming edges will have some weights. The sum of all the weights of incoming edges should be equal to the sum of weights of outgoing edges. So So this is flow conservation requirement. So the total number of material leaving the source must end up with the sink. So all the material leaving from the source node, ultimately they go to sink. So they must end up with a sink node or destination node. There are two constraints in maximum flow problem. One is flow conservation constraints and another one is capacity constraints. As previously discussed, the flow conservation constraints is nothing but incoming flow is equal to the outgoing flow for every vertex except the source and destination node S and T. The capacity constraints is nothing but flow on an edge does not exceed the given capacity of the edge. Means in this example, this edge from 1 to 2 has the capacity of 2. So the flow should not exceed this capacity. So this is called capacity constraints. So the ultimate objective of this maximum flow problem is stated as maximization problem, where maximum flow must be achieved through the network from the source. So this is maximization problem, which actually detects the maximum flow through the network from source to destination. So this is achieved by Ford-Fulkerson algorithm or augmenting path method. The other name for the Ford-Fulkerson algorithm is augmenting path method. So what is augmenting path? Let us discuss in the next slide. There are some basic terminologies used in this Ford-Fulkerson method. So what are those terminologies? The first one is augmenting path. It is nothing but a simple path from source to destination in a graph. So it is easily understood. A simple path from one node to another node. Obviously there may be a path from one node to another node, but augmenting path means from source node to destination node there should be a continuous path. Either it may be a forward edge path or a reverse edge path. That's called augmenting path. So what is the residual capacity? Residual capacity is nothing but original capacity of the node, original capacity of edge minus current flow. So obviously all the edges will have some numeric values. Those values are called the original capacity. The residual capacity is nothing but the original capacity minus current flow. The third one is residual graph. It is a graph which indicates additional possible flow. Additional possible flow means if there is a possibility of constructing an augmenting path from source to destination, then naturally we will add the flow to that node. What is minimal cut? So minimal cut is nothing but it is a minimum value which gives the maximum flow. So it is also known as bottleneck capacity, which decides the maximum possible flow from source to sink through an augmenting path. So all these terminologies we will discuss in the example. The augmenting path can be done in two ways. One is non-full forward edges and another one is a non-empty backward edges. If it is a forward edge, the augmenting path contains only forward edges. Forward edges means the arrow mark will be towards the positive direction. It's called forward edges. The condition is it should be non-full. So non-full means something should be left. It should not be full. Whereas non-empty means it should not be zero. Some numerical value should be there. Then only the augmenting path will be possible. This Ford-Fulkerson algorithm consists of 3 steps. The first step is start with an initial flow of 0. So in the diagram given, initially the flow is considered as 0. While there is an augmenting path from source to sink, then add this path flow to flow. So initially the flow is 0. If there is any augmenting path, then the current flow of the path is added to the flow, then the flow is updated then and there. Now return the flow value. So this is the steps involved in Ford-Fulkerson algorithm. Now we will go for an example. So like this, a graph will be given in the question, a diagram will be given which contains several nodes. So in this graph, S is the source node and T is the destination node, which is otherwise called sink. And there are some intermediate nodes A, B, C, D, and their weights are given. As I said, the initial flow is considered as 0. So the initial flow is 0. Therefore, the capacity is written as 0 by 10. So it means 0 means flow. Since the initial flow is 0, it is written as 0 by 10. 10 means the original capacity of the edge. So like this, all the edges are written like this as the initial step. The next step is find the augmenting path from source to destination. I told you it may be a forward edge path or it may be a reverse edge path. Now consider from source node S to the sink node T, there is an augment path which involves all the forward edges. Say S to A to D, D to T. So my augmenting path is now S, A, D, T. So these augmenting path can be arbitrarily chosen. So any augmenting path you can take. There may be n number of augmenting paths. You deduct one by one and write it. So the first augmenting path in this diagram I have chosen is SADT. Next thing is we have to find the bottleneck capacity. Okay, so assume from S to A the original capacity is 10. It means that the flow, maximum flow possible from S to A is 10. From A to D the maximum possible flow is 8, and from D to T the maximum possible flow is 10. So 10, 8, 10. So which is the minimum value? 8 is the minimum value, because from A to D only we can pass 8. So this is considered as the bottleneck capacity. Okay, so bottleneck capacity is written as 8. Now we have to update this values in the next graph. So this is my residual graph obtained and the flow value is updated here. Since my bottleneck capacity is 8, it is added with the flow value. So my initial flow is 0. Now the bottleneck capacity is 8. This 8 is added to the current flow. So 0 plus 8 is 8. 0 plus 8 is 8. 0 plus 8 is 8. So 8 by 10, 8 by 8, 8 by 10 we are getting. See here, it is 8 by 8. It is 8 by 8. It means that, so all the data flow through A to T. It is full. It has become full. So there is no possibility of considering this edge AD hereafter. Okay, since it is full. So our condition is, if we consider the forward edge path, it should be non-full, but it is full here. So we should not consider hereafter. Okay. Now my residual capacity here is 2, 0, and 2. Okay. What is the residual capacity? The original capacity minus flow. Okay. So in this way we can calculate the residual capacity. So now the flow value is updated as 8 because my bottleneck capacity is 8. So initially it was 0. So 0 plus 8 is 8. So like this, in every augmenting path the flow value must be updated. So this is my second augmenting path. Now I am taking SCDT. Similarly, in the same way I am calculating the bottleneck capacity here also. So here it is original capacity is 10, 9 and 10. The maximum value or maximum flow that can be passed through one node to another node is only 2 here. See, here it is 10, here it is 9, here it is 2. Why 2? Already we have passed the 8, the remaining 2 is left, so that will be the residual capacity. So we have to consider only the residual capacity, not the flow. Okay, so only 2 can be passed here, so that should be the bottleneck capacity, so minimum value. So that is written here. So my augmenting path is SCDT, my bottleneck capacity is 2. So this 2 must be updated here. So it is added since it is forward edges. So 2 plus 0 is 2, so 2 by 10. 2 plus 0 is 2, 2 by 9. And 8 plus 2 is 10, 10 by 10. Here it is become full. So we should not consider this edge hereafter. And finally the flow value is updated. Initially it was 8 and now it is 2 added with the 8, so the flow value become 10. So this is my third augmenting path, SCDABT. SCDABT. So S to C, it is a forward edge. C to D, it is a forward edge. Whereas D to A, it is a reverse edge. A to B is a forward edge. So now we have to find the bottleneck capacity. From S to C, the residual capacity is 8. C to D, the residual capacity is 7. Whereas D to A, it is 0. The residual capacity is 0, but the capacity is 8. Since it is a reverse edge, what is the condition for reverse edge? It's non-empty. It is not empty. It has some value, numerical value 8. So it is not empty. So we can consider this reverse path. Here the residual capacity is 4. Here the residual capacity is 10. So 10, 4, 8, 7 and 8. So among these 5 values, 4 is the minimum value. So bottleneck capacity is 4. So this is updated here. So 4 is added to 2 since it is a forward edge. So 6 by 10. Here 6 by 9. Here when you come across a reverse path, instead of adding, it should be subtracted. So from 8, 4 is subtracted, so 4 by 8. Since it is a forward edge, it is added, so 4 by 4 and 4 by 10. So this current flow 4 is updated here. So initially the flow was 10, now it is 10 plus 4, 14. And we have to find, is there any other augmenting path in the graph left? Yes, we have one more path, that is SADBT. So all are forward edges. Here the bottleneck capacity is found as 2 because the residual capacity is 2 here, 4, 6, 6, so 6, 6, 4, 2. So the bottleneck capacity is 2. This is updated here. So 8 plus 2 is 10, 4 plus 2 is 6, 0 plus 2 is 2, and 4 plus 2 is 6. And this bottleneck capacity 2 is added to the flow and it is updated as 60. So I should check whether there is any further augmenting path in the diagram. See, look at this edge. So 4 is left because only 6 has been flowed. So 4 is left. So we can consider this. Here also we can consider this because 3 is left. Here 4 is left, and here 4 is left. So I can take this path. So now my augmenting path is SCTBT. The bottleneck capacity here is found as 3, and this is updated as in the previous cases, and now the flow value becomes 19. Okay. You can correlate this final diagram with the constraints. So what are the two constraints in maximum flow problem? One is capacity constraints and flow conservation. Flow conservation means if any node is having the incoming edge, or incoming flow value of any node should be equal to the outgoing flow. So this is called flow conservation constraint. So incoming flow of any node should be equal to the outgoing flow of node. See, take this. So this should be considered except S and T. So intermediate nodes only we have to consider, and these constraints are satisfied with these 4 nodes A, B, C, D. So look at C. What is the incoming flow to this node? 9. What is the outgoing flow from C? 9. So incoming 9, outgoing 9. Satisfied. Consider B. What is the incoming to B? It is 4. It is 4. And from D to B also 5 is coming. Okay. So from A as well as D, these two edges give 4 plus 5, 9. So the incoming flow is 4 plus 5, 9 to B. The outgoing flow is 9. So like this, all the 4 nodes A, B, C, D must satisfy the flow conservation requirements. So apart from this augmenting path, there is no augmenting path further can be drawn with this diagram, because here one is left. We can consider this edge from S, but from C this is blocked because 9 by 9 it is full. We cannot go like this. We cannot consider this reverse edge also because already it becomes 0. So our condition for reverse edge is it should not be empty, non-empty. Okay, but here it is empty. So this is also blocked. Here S to A already 10 is reached. It is full. So there is no augmenting path further. So up to this we can stop, and the maximum flow through this entire network from source to destination is 90. So this is the result we achieved. After achieving the result, we can tabulate all the values and augmenting path. These are the 5 augmenting paths I have taken in this problem, and this is the bottleneck capacity. You sum up all the bottleneck capacity to find the maximum flow. So 8 plus 2 plus 4 plus 2 plus 3 will give you 19. So this is the answer. This is the maximum flow for the given graph. Thank you for watching.